I will talk into this one. Okay, cool. Great. Hi, everyone. My name is Aaron Cunningham. As Jason said, I'm based in Singapore. I've been at Google for 11 years now. As a program manager, I focus on all of our open source chip design and EDA tools. So it's great to be here with you all. I heard there's a huge comic expo and GamersCon going on also right now. So thank you all for being here with me instead of over there, but I may go afterward. Okay, so this is sort of a high-level introduction to our programs and what we've been doing. So for those who aren't familiar with sort of how Google works, at the high level, generally, our entire business has been built on this concept of buying regular, off-the-shelf consumer processors in large scale and clustering them together and using them to run all of our compute infrastructure for every workload, whether it's search or emails, YouTube, everything just runs on one giant cluster computer of all regular processors. So we have a very, I think, well-known paper, sort of how that all came together back in 2003. And this has worked out well for us for the last 20 years without too much issue. The problem we're having now is that, as you may all be familiar, Moore's law is beginning to slow, such that every year we would just go and buy the latest and greatest processors and add them to our cluster, and every year they get faster and faster. But these aren't getting as fast year to year as they did before. So the performance is beginning to slow down. Meanwhile, our need for power is continuing to increase as our services grow larger and larger. And so here's an example of a graph that is displaying the red line is the amount of video that is uploaded to YouTube. I believe that is every minute, or hours. Yeah, hours uploaded every minute. And that is growing faster than our compute infrastructure can compress it to store it. And so if anyone here, if you're a YouTuber and you've uploaded a video, you might see a little spinning dial as you're waiting for your video to be processed. That waiting time has been getting longer over time because YouTube is getting more popular. That's a challenge that we needed to solve internally for ourselves. So what we did at Google is we actually built our own custom ASIC that does nothing except compress video. That's all it does. And this is interesting for us because this is a departure from our regular model of a single cluster that's giant with regular x86 processors. We now have these smaller clusters that are dedicated to a specific workload. So in this case, we're only compressing video. We're applying this approach to other unique workloads as well as our demand is scaling. So you may have heard we have what's called a TPU, or tensor processing unit. We have clusters of these that do the same thing for machine learning. We expect to see, I think, more of these in the future as we find more specialized workloads that our current cluster is not well equipped to do at scale. So as you know, Google is a very large company. We are pursuing many, many parallel efforts to attack these problems and try to understand them and make improvements. So, for example, many of our more near-term demands, like the VCU for compression example I just noted, we're using regular traditional ASIC design flows that you would normally see with proprietary tools, using modern production nodes. It's all very normal. We have other groups that are exploring other opportunities here as well. Can we use AI to drive design and synthesis and floor planning in the design flow? We don't know yet. I think we're seeing good progress there. We're continuing to work. The effort I'm here to discuss today is what my team does, which is another more long-term investment where we're looking at how we can create open source design tools to build an ecosystem that supports research to continue solving these problems. So the program I'm discussing here has three main components. I'm going to talk about open source PDKs, the open source tool chain that we're currently working with, and then a manufacturing effort to sort of realize these and to prove to ourselves that the tools mostly work. And there we go. Okay, so first, for those who don't design hardware, a PDK is a very basic starting point. These are the basic building blocks for designing custom chips in a foundry. So the foundry typically provides this to you. These can be thought of as design rules. If you want to make a chip in their factory, you must fit inside of this specific size. There are these features available to you. They have this level of performance. And these are all useful for you as you're creating your design. The problem that we've seen with these in the context of research is that they often have very restrictive licenses, because naturally, a large foundry doesn't necessarily want this getting out to everybody, because that could create issues for them. So generally, you have to license it, you have to sign a non-disclosure agreement, you have to agree that you won't share this information with anybody else, and you'll only use it for yourself. We've seen issues with this around research specifically, because especially where Google is headquartered in the United States, the universities are not well connected to each other. And it's very difficult for universities to collaborate with each other, because if one university publishes a paper and they share their results, it's very difficult for another university to reproduce those results, because they would need to license access to the exact same PDK and the exact same IP. And so often you'll see papers that are published, and yes, they are peer-reviewed, but it's very difficult for anyone to actually prove the point that was made unless they can go and create the exact same chip. And unless they have all of the same components existing that they've licensed access to, they're going to struggle. So to try to solve this, we've approached 2 foundries so far. We worked with Skywater, which is a small foundry based in the United States. I've also worked with Global Foundries, which is a little bit larger, to start with 2 PDKs to release under open source licenses. So Skywater has agreed to release their 130 nanometer process, and then Global Foundries has agreed to start with their 180 nanometer MCU process. But I also want to call out here specifically IHP. Google had nothing to do with them releasing their PDK, but we're really excited to see it, because we think more open PDKs that are available are better, because that gives the tools more opportunities to be tested and prove to show that they work. So now that we have PDKs available, we need tools that can work with them. And so there are many, many open source projects that exist in the space to address each step in the flow. I know that Frank noted in his presentation earlier this morning, these are all very disconnected, and it's very difficult to chain them together into a single coherent flow, because each open source project run by volunteers, they all pick a different part of the problem to solve. And so at Google, we're interested in trying to identify these different projects in the ecosystem and support their researchers via academic grants. So if anyone in this room is working on related tools in the space, please reach out to the university relations team. We would love to talk to you. But our goal for our research projects has been to integrate these into an end-to-end tool chain. Try to fill in the gaps that we notice with our own contributions from our software engineers, or we work with industry partners via groups like the CHIPS Alliance to find other large companies who are willing to pitch in here and help and try to make this better. So our high-level tool workflow that we're experimenting with right now is we're starting with a tool that we work on called XLS, which is a high-level synthesis tool, feeding that through Yosis for synthesis, into OpenRoad or OpenLane to do place and route, and then Magic and K layout at the very last step to end up with some GDS that we can send to a foundry. Our flow is much more detailed than this. However, I'm just the program manager. I'm not the software engineer. So my colleagues can explain this in much more detail if you want more information. OK, so we've established we have PDKs and now tools that mostly work that we can chain together to work with them and create designs. We wanted to prove to ourselves that these tools would work to create actual silicon. And so what we wanted to do was try to create as many chip designs as possible to feed through the system. I think earlier presentation you noted pipe cleaning, which is great to prove everything is good by just running as many designs as we can. The problem that we have is that we're a small team. We only, even as Google as a whole, we only design a few chips every year. So by creating an open multi-project wafer shuttle program, our goal was to basically provide free manufacturing for the ecosystem. Anybody who wanted to use the tools to create a design could submit their design to our program, and we would manufacture it for them for free. And what this got for us was, instead of just a few dozen engineers creating designs, we had hundreds or thousands of engineers creating designs that we could then run through the system to test and find bugs and find corner cases that did not work the way we expected. So the requirements were very simple. There was no cost. However, your design must be open source. It must be reproducible. So all of the artifacts must exist in a GitHub repo so that somebody else could also create your design. And then we would select 40 projects for each run, because that was the number of slots we had available on the wafer at the foundry. So to facilitate this in a way that would work at scale, each designer was provided with a common harness to start from that incorporated a RISC-V core, which is shown here in this diagram at the top. That provides all of the basic control, power, and I/O. And then a whole empty space for you, the designer, to fill with whatever logic you wanted to design using the open source tools. It looks like, oh, there we go. Okay. I need to move my mouse to get the image to appear. So this is what it looks like in practice. We have a small area of the footprint up here, which is sort of the management and maintenance functions, and then a giant empty space for anyone to fill with what they wanted. Since we began this in 2020, there we go. The program has run 8 shuttles so far. We've received over 600 submissions from 19 different countries. And we've also been really excited because this has served to raise awareness and drive adoption of these tools. This helps us because the more people that use the tools, the more bugs we find, the quicker we can fix those bugs because we get contributions from the ecosystem. And everybody helps everybody else improve these much faster than they would if we were trying to do it on our own. However, it has not been perfect. For those that have followed along, we have encountered many challenges because I don't think this has really been done before at this scale with open source tools in a large community like this. So our first shuttle that we ran, MPW-1, the common harness was flawed. And so everybody who received their first taped out chips didn't work. So we had to work backwards a little bit and try to fix the harness. We got them mostly working. There are actually some great YouTube videos that you can follow along where participants have sort of taken us through the process they took to fix their designs. Our documentation still needs improvement. Like this is all still a work in progress. And the shuttles are still in process. I mentioned we've launched 8 so far. We've only gotten the first 3 back. And the third one, I think, only came back this past month. So we still have, I think, 5 more in flight that we're waiting to come back from the foundry. So we're still working on this. But each shuttle, we think, is getting better than the one before. So MPW-2 was finished and delivered in June. So this was as of a little over a month ago. We had 40 different projects all submitted. These are all of them alive and blinking on their test benches. And so I have a few examples I can share of some fun ones that we saw from the second group. The first, this project is called Yi-5. It is a 32-bit RISC-V core with some SD-RAM and a memory controller and quad SPI. This is from a professional SoC designer at Intel who just really liked the program and wanted to do a personal project for fun to try to make his own chip using the tools. And it worked, and it's good. I don't know how performant it is. I'd have to go ask them about what their performance numbers look like, but as a proof of concept, we think it's really exciting. Next, this group is called Fabulous. This was a student at Heidelberg University, and she was working on an FPGA fabric implemented on this custom silicon. And so there's a number of gates there. And we think that worked because showing a demo here. This one I think is also really entertaining. Let me go back. There we go. So we told everybody there were 40 slots available on each shuttle run, and we could only pick 40 projects to put on. So what this person, Matt, did, he actually teaches a course called the Zero to ASIC course, which you can find online. And he walks you through how to use all of the open source tools. Even if you have never designed a chip before, you can take his course and he will teach you how to make your own chip. And so what he does is he takes all of his students' designs and combines them together into a single project that then gets submitted to the shuttle program. So he actually has 16 different designs implemented here, trying to maximize the amount of space available in the project. Instead of trying to submit 16 different projects, he just collects them all together, which is a really great way to cheat the system, I think, and try to get more manufacturing done. This one is called Space Shuttle. This person is working on research around radiation hardening. And so they've set up some register files here with an ECC and designed it in such a way that it is more resistant to radiation and outside forces. And then taking the previous example to its sort of logical extreme, Tiny Tape-Out is another effort that also teaches chip design at a much smaller scale. So these are very simple functions. But they're actually fitting 200 different student submissions into a single design that then gets taped out. So if you participate and you create a design and you submit it, you might end up with that spot. But you'll still get a chip back from the foundry, and you can plug it in and see, and you can verify that your little spot worked the way you thought it would, which we think is also really exciting. Because for many people, especially students, your first experience doing chip design won't actually happen until after you've graduated. I know it's much better here in Taiwan. You have so many more programs available to you here. But in many other countries, especially in the US, you typically need to find a job first before you can really get a lot of experience working with silicon. And so this allows students in secondary school to be able to get silicon back in their hand. We think that's really amazing and impressive. Other related efforts that are going on here, we've partnered with NIST, which is a research organization in the US that's funded by the US government. They have a need for nanotechnology research that they want to perform. And they needed a physical substrate upon which to build their nanostructures. And it turns out planarized wafers are perfect for that because they're already very flat. And so they have migrated one of their designs for a planarized wafer for nanotechnology construction over to the Sky 130 node, which then allows academic researchers to purchase entire flat wafers at cost to then develop their own nanostructure they can build on top. So this has been a really exciting program. I think they're starting to ship now, if not already. So yeah, this is fun. And then I think we've also been really excited to see the impact we've had on education so far. I think I mentioned earlier, in other countries, many students don't gain access to these things until after they've graduated. But now that the tools are mostly working and available free of cost, it's much, much easier for smaller universities to gain access to these things and actually begin manufacturing. So Stanford has adopted these tools for their electronics engineering course. The IEEE has launched a chipathon for students that is built on this platform. IIT Bangalore is using it for their undergraduate students as well. So we're excited to see more people diving into this to actually create curriculum, and then, of course, find bugs and file them so we can fix them. So in terms of next steps and what we're trying to do from Google's perspective, our first thing is, I think we've demonstrated this as an example of subsidized shuttle programs are a great way to get more silicon into more people's hands. But we are not enough as Google to do this by ourselves. And so my goal is to help other groups replicate our success with other foundries, other processes, other schools, anyone who's interested here. I'm excited to see, I think, especially as more governments get involved here, because they see the value in developing their own domestic startup ecosystems by helping startups get access to this stuff much faster. In doing that, we want to help others avoid the traps that we found along the way, because doing these things is not easy. We've learned a lot. And then we've also, as we've discussed, we want to fund more research in this area for anyone who's working on tooling here. We think there's a lot more that can be done. Especially, my team specifically is focused a lot on high-level synthesis for accelerators and hardware-software co-design. So if you're a researcher in this area, come talk to me. I'd love to meet you. And then for more resources, we have a very large Slack community with almost 5,000 members. There are hundreds of channels in there, I think, for different parts and tools. So definitely recommend joining that. We also have our own developers website, developers.google.com/silicon. And then the synthesis tool I mentioned earlier is called XLS. So that is on GitHub as well. And that's the end of my slides. So thank you. Does anybody have any questions? Oh, wait one. Thank you.
Thank you for your presentation. I have one question. For the MP project, at first, I have to my background. I will talk in this later session, but I teach to children, junior school to junior high school, and my supporting foundation requests us to make the program to produce chip for children, and the big problem is latency. When tape out to get back the chip, actually for the Skywater project, how long does it take to get chip?
Okay, so the question was, if you're submitting a design to the shuttle program, how long does it take for you to actually get finished silicon back? I don't have a good answer because, well, if you can chime in.
Yeah, it takes about 6 to 9 months depending upon. It takes about 6 to 9 months depending upon which Skywater shuttle you get on. So it's not short. And right now the shuttles are not. They're backed up, as you mentioned. So you're looking at about 9 months. The last tape out we did through Skywater, I think it was close to a year. I haven't tested the silicon. I don't know if it works.
Yeah, and that reflects the lessons that we've learned in doing this program. Is the first MPW1 that we launched, it took over a year before we got anything back. MPW2, I think we got that shortened to a little under a year. Yeah. MPW3 came after that. That was also a little less than a year. We're expecting 4 through 8 to arrive before December is what we're being quoted right now. So we should finish the remainder this year. And we're currently waiting to see how those end up before we decide what next shuttles will look like.
Normal process should be 5 months.
Yeah, ideally, we should be at like 5 months. I think when we worked with Global Foundries, we did a test run with them on their 180, and we got that one back much, much faster. I think our turnaround for that was only 2 months. So I think the more that this works, the better we'll get. And so we're hoping that as more people sort of take on this effort, we'll see that accelerate. Question over here.
Yeah, thank you. Thank you for your team's effort. It's very informative. And I got 2 quick questions. The first one might be sensitive, but let's take it easy. I see that this is a project from Google, but I also see there's some engineer from non-Google company also involved. So is it okay for all around the world, not just only for the university program, to get involved to use this project? And second question is that after you get a real chip, yeah, speaking of the reproduce, right? So we also need to do the validation. So is there any information you can share more how you do the validation with the real chip?
Cool. Okay, so the first question was, who can participate in shuttle programs? The way Google ran ours, because our position was based on open source, it was open to anybody who wanted to participate. So for our first shuttle run, We had some submissions from university students. We had some from hobbyists. We had somebody making a crypto accelerator, because there's always at least one in every group. We had some people doing amateur satellite radios. And then we had commercial groups as well. Western Digital taped out a chip. IBM taped out an open power chip as well. So there were no restrictions. The only challenge is your design must be open source. So if you were a startup, for example, and you wanted your chip design to remain secret, this would not be a good option. But our partner who runs the shuttle program, eFabless, they have a separate commercial shuttle program for those, where you can submit your design, it remains secret, they go and manufacture it and then send it back to you. So there are options for both, but the free one required that you have to be open and you have to share your design, because reproducibility is what we wanted to fix. The second question is, how do you handle bring up and testing and validation of your silicon? We don't have a good standardized solution for that yet. Currently, with the current shuttles, you will get, I think, a quantity 50 of the bare dies back, but then you also receive a number of breakout boards that you can mount your chips onto to do some basic testing using the RISC-V core for I/O. But we've seen different groups take on their own sort of process for that. Some people use pogo pins, some people like 3D print their own little fittings. We're sort of watching to see what the ecosystem comes up with. Another question.
Yeah, so full disclosure, we did a commercial tape out through eFabless. It was a pretty good process. What I'd like to ask is, how is Google validating the tools? And are you allocating money to make sure that the tool outputs are correct and validated against commercial tools, so that we know that, for instance, extraction is correct, that timing closure is going to do what you expect, all of these things. To be clear, right, when we did the tape out, I took a look and I'm like, not going to work, and it doesn't. We knew that. There was no place for us to like grab you. So how do we do that as the second part of the question?
Very good questions. Okay, so the first question was, what is Google doing to really validate the open source tools themselves and prove that they work? And the PDK. There's a couple of things. One, we do try to support as many of the open source tools as we can as part of the flow. We have financial grants and money that we pay. We also contribute lots of time from our software engineers submitting patches and pull requests where we find issues. In terms of validating the PDK, it's a really interesting problem. We've started to engage with groups like NIST to perform characterization. The great thing about having an open source PDK is that when you have a group like NIST do cryogenic characterization, for example, they can now actually share those results. And so we're looking forward to having more of that available. Is it out yet? No. And that's where the documentation needs to improve. We still have a lot of work we need to do, which is why we want to see sort of how these first 8 shuttles work out.
At the end of our process, we thought to ourselves, what we should do is pull that tape out and do test structures only. We should do a ring oscillator. We should make, a counter. We should do all these things, and we just didn't get there on time. That's a simple thing. There's no need for NIST. Like somebody like Google's engineers themselves can sit down and make a small chip that does those kinds of things. I assume you have people that know how, right?
Yes, and some of them were on later shuttles that haven't come back yet. But yes, great. So I want to be respectful of time. Rinland, are we okay?
We're 5 minutes next to the Jiang talk. So
Okay.
maybe. Okay, one last call.
Okay.
One last question.
Otherwise, yeah, come find me. I'll be in the hallway.
And I think that we can set up the level.
I want to know the free MPW shuttle continue. I see the MPW 9 is stopped this year.
Okay, so the question was, will the shuttle program continue? The answer is we haven't decided yet. We're waiting to see what the first 8 look like to decide, okay, does it make sense for Google to continue doing this? Can we find some industry participation to grow it much larger than just Google? Those are many options that we're exploring right now. But for right now, the answer is we don't know yet. So anyway, thank you, everyone.
Thank you so much. And we are